Moving charged particles create magnetic fields. If a charged particle moves in a magnetic field, the charged particle experiences a magnetic force. This force is greatest when the particle moves in a direction perpendicular to the magnetic field lines. At other angles, the force is less. The force becomes zero when the particle moves parallel to the field lines. The direction of the force is always perpendicular to both the magnetic field lines and the velocity of the charged particle. Charged particles from outer space are deflected by Earth's magnetic field, which slightly reduces the intensity of cosmic radiation. If charged particles are moving inside a wire, the wire will also move. If the direction of current in the wire is reversed, the deflecting force acts in the opposite direction. The force is perpendicular to both the field lines and current, and it is a sideways force. The discovery that a magnet exerts a force on a current-carrying wire created much excitement. People began harnessing this force for useful purposes: electric meters and electric motors. The simplest meter to detect electric current consists of a magnetic needle on a pivot at the center of loops of insulated wire. When an electric current passes through the coil, magnetic forces deflect the needle. A sensitive current indicating instrument is called a galvanometer. The coil is mounted for movement and the magnet is held stationary. If the design of the galvanometer is slightly modified, you have an electric motor. The principal difference is that in an electric motor, the current changes direction every time the coil makes a half revolution. After it has been forced to rotate one half revolution, it overshoots just in time for the current to reverse. The coil is forced to continue another half revolution and produces continuous rotation. In a simple DC motor, a permanent magnet produces a magnetic field in a region where a rectangular loop of wire is mounted. The loop can turn about an axis. When a current passes through the loop, it flows in opposite directions in the upper and lower sides of the loop. The loop is forced to move as if it were a galvanometer. The current is reversed during each half revolution by means of stationary contacts on the shaft. The current in the loop alternates so that the forces in the upper and lower regions do not change directions as the loop rotates. The rotation is continuous as long as current is supplied. The compass aligns with the magnetic field of Earth, but the magnetic poles of Earth do not coincide with the geographic poles. The magnetic pole in the northern hemisphere, for example, is located some 800 kilometers from the geographic North Pole. This means that compasses do not generally point to true north. The discrepancy is known as the magnetic declination. The configuration of Earth's magnetic field is like that of a strong bar magnet placed near the center of Earth. Earth is not a magnetized chunk of iron like a bar magnet. It's too hot for individual atoms to remain aligned. Currents in the molten part of Earth beneath the crust provide a better explanation for Earth's magnetic field. Most geologists think that moving charges looping around within Earth create its magnetic field. Because of Earth's great size, the speed of charges would have to be less than 1 millimeter per second to account for the field. Another possible cause for Earth's magnetic field is convection currents from the rising heat of Earth's core. Perhaps such convection currents combined with the rotational effects of Earth produce Earth's magnetic field. The magnetic field of Earth is not stable. Magnetic rock strata show that it's flip-flopped throughout geologic time. Alternating magnetic stripes in rock on the ocean's floor show that there have been times when the Earth's magnetic field has dropped to zero and then reversed. More than 20 reversals have taken place in the past 5 million years. The most recent occurred 780,000 years ago. We can't predict when the next reversal will occur because the reversal sequence isn't regular. Recent measurements show that a decrease of over 5% of Earth's magnetic field strength in the last 100 years. If this change is maintained, there may be another field reversal within 2,000 years.